Word.
Welcome to the .NET User Group. Tonight's speaker is Matthew Hess. Matthew Hess, aka the C# Artisan, is a software engineer from Albuquerque, New Mexico, and the organizer of the Albuquerque .NET Users Group. Matthew got his start programming using Borland's Delphi IDE and the Pascal language, and has been working with C# and the .NET framework since version 2. Matthew has written software for many different industries, from legal to financial services to biotechnology to nonprofit. His YouTube channel, at C# Artisan, is meant to help programmers of all levels become better at the craft of programming in C#. Matthew, take it away. You got to unmute. Can you unmute, Matt? And then
You're on mute. Can't hear you.
How's that? Is that a little better?
Much better.
Yay. Where's the mute button? That's going to be a feature we implement. Okay, let me share my desktop and let me start my slides. And let me switch because it puts them on the wrong. There we go. Okay, so today's talk is called, first of all, can everyone see the content? Is that okay?
Matthew, when would you like to receive questions? Would you like us to wait to the end or interrupt you or put in the chat? How would you like those?
So I actually can see your faces, and I can see if somebody puts their hand up or waves a little, I will absolutely interrupt in the middle and take questions as we go. And I also kind of stop at given points to check in. So there'll be natural places for that. I think right now, Elsa, would be a little early for a question, but that didn't stop you from sneaking one in right there. I saw that. That was good. So,
all right.
And I just demonstrated that I can kind of roll with it and go with it. So I think we'll be good. Yeah. If you have a question, raise your hand, chime in. This is meant to be interactive.
Very good. Thank you.
The talk is called Wait, What? Async-Await Explained. And I just want to ask a quick question. How many of you have written C# that included an async-await statement? Everyone turned their camera off, but like usually when I ask this, like 90% of the people in the room are like, yeah. So it's just like bread and butter, right? We do this all the time. It's foundational C# language feature. And as I'll explain, I honestly think many of us really don't know what it does or why it exists, which might seem like a controversial statement up front for me to just insult everybody in the room and tell you don't know what you're doing. But really what happened is I had kind of a wait what moment where I was like, I really don't feel like I quite get this. And I went through my own kind of personal journey of unpacking it and discovery. And so that's what I want to do today, is kind of take you all through that. And maybe at the end, you'll be like, oh, that was kind of interesting. I learned something. Or maybe you'll be like, I knew that all along, but you have a nice shirt anyway, so it wasn't a total waste of time. So, but before I dive into that, I just do want to do a couple of acknowledgements. First, I always have to thank my Uncle Mel. Honestly, I just don't know where I'd be in this world if it weren't for you, Uncle Mel. You mean the world to me, so thank you. That was a joke, by the way, so I hope you're all quietly laughing. It's fine. I also want to thank my employer, CG Infinity. It's a consulting shop out of Plano, Texas. And honestly, a really enlightened, great place to work. They are super supportive of these kinds of activities. They sponsor the Albuquerque.NET Users Group. So thank you very much, CG Infinity. And thanks to all of you, Twin Cities.NET User Group. I'm really glad you showed up. I'm a little sad I couldn't come in person. I spent one glorious winter living in St. Paul. And so I love the Twin Cities, especially the weather. But virtual is good too. So thank you all for showing up and for maintaining these .NET user groups, which some of them have had a little rough patch recently. So a few words about me and like why I'm even bothering with this, what we're doing. And I want to begin by like posing this question that often people ask, software development. Is it an art or is it a science? Art or science? And to me, it's neither. It's something else. So don't get me wrong. I believe that computer science is a real thing, that there are people, extremely smart people out there researching the cutting edges of computer science and developing quantum computers and AI algorithms and stuff. They're incredibly smart. I have count a few of these people as friends. And if I put a few beers in them and slow their brains down a little, we can actually talk and relate. But that's not me. I'm not a super genius computer scientist. Hats off to them. And I think most of us probably experience when you write nice code or well-architected code, there is an artistic element to it. It's aesthetically pleasing. So there's the art side of it. But for me, over the years, week in, week out, year in, year out, I've been paid to just build stuff that works. So it's more of a craft, at least what I do. And so that's why I use this little moniker, the C# artisan. I view programming as artisanal, it's a craft. And I kind of am doing this work, this outreach and education, just to kind of help us all level up. Anyone can like use GitHub Copilot and, write out some decent code, it'll be okay. But for things to be really good and next level and really, professional, I still think it takes a certain amount of HI, human intelligence, and it's a craft that we work on. So that's why I'm here. And that's what I hope you'll get out of this is just a little insight in how to be a little better as a C# programmer. If by the end of today, you're not completely sick of me and you think, hey, I might want to interact with that guy or see more of his videos, feel free to hit me up on LinkedIn. I would love it if you'd go to my channel at C# Artisan, subscribe, watch the videos, like them, do all that cool stuff. There's a lot there. So this is the moment where you can take a screenshot if you want, and that way you'll have those QR codes for later. I do have this Gmail that I occasionally check as well, but the other ways are better ways to get a hold of me. Okay, so that's a little about me. Sorry?
Gotta squeeze out those poops.
Okay.
Someone's got a toddler at home.
I'm like, Chris, we might have to do that later, but I'm open-minded, so that's fine. I'm not gonna complain. Okay, so let's get into the main talk here. There's the async-await stuff. So what is the point of asynchronous programming in the first place? Why do we do this kind of stuff? And at a very core level, async programming in all the different flavors is just about allowing your code to do more than one thing at a time. You want your code to do more than one thing. Now, there are a lot of terms and paradigms that people use when talking about this. You maybe hear about parallel programming or concurrent programming or multi-threading or asynchronous programming. And they're all kind of conceptually related in that they all allow your code to multitask in various ways. So asynchronous programming is a very specific flavor of this. And the point of asynchronous programming specifically is it focuses on letting your code stay busy or responsive while you're waiting for a longer process to complete. So it's a little different than like strict multi-threading or other things, though again, these concepts overlap. So that's a kind of abstract definition, letting your code stay responsive or busy while you're waiting on a longer process. So to bring it down to reality, I always like to talk about food. Food is highly motivational for me. And so I would like to illustrate this point with a little story called Dinner in Kyoto. So let's say you're in Kyoto. I was there last October, amazing city, highly recommend it. And let's say you're hungry, you'd like dinner. So you walk into one of any number of restaurants and you encounter this machine, this interesting kiosk So it's a very cash-oriented society. And what you do is you make some selections on the kiosk, you feed in your cash, you push a button, it prints out a little ticket for you. And it also prints out a ticket, or sometimes you just run it over and hand it to the people in the kitchen. So then they prepare your food, and eventually your food is ready, and you go present your ticket, and they hand you your food. So that's how you order dinner in Kyoto. But let's say, for the sake of argument, that you were also thirsty. Not only did you want dinner, but you wanted a drink. So in the real world, what you would do is, after you placed your order and while they were cooking, you would leave the store, you'd wander down the street to one of 10 million coin-op vending machines that are in Japanese cities. You'd put in 100 yen, and for 1 coin, you would get a bottle of happiness. You'd pick your interesting Japanese soda, and you would take it back to the restaurant. And whoop, I went too fast. You'd take it back, and then you'd sit down with your food and your drink, and you would enjoy dinner. So let's model this real world interaction as a UML sequence diagram. This first UML sequence diagram shows if we did it synchronously, no async here. So the first thing that would happen is we would call a function called order food. We would address the order food server, we'd call a function, and we would wait for order food to return. And then our katsu would come back and we'd have our dinner. Then we would call a second function called get drink. And then it would return, and then we'd have our food and our drink, and we would enjoy them. So that's synchronous, right? Fairly straightforward. But that's not really the story I told. What I told was the asynchronous implementation, where those two things are overlapped. So you call execute async, you order food async, and then immediately you get drink async. And both of those kind of run overlapped. And we don't know which one will return first. We're just going to await them both. And when they come back, our drink and our dinner, then we enjoy our food. So that's what the asynchronous call pattern looks like. And this is kind of what we want, right? The point is to let our code do more than one thing at a time, be overlapped. So we're going to translate this to C# in a moment and see what happens. Okay, so let's now write some C# code that implements this. And again, it's to kind of, boilerplate code, but we have our little HTTP client instance that we're sharing, and our main function is called get dinner in Kyoto. And we say, okay, my dinner equals await order dinner. So that's an async function here, which calls some server, the restaurantkiosk.com. It says, I want item 29, options is rice. It checks to see, did we get a status code? Then it deserializes your dinner and returns it. So now we have a dinner. And then we say drink equals await order drink. And again, we call out to drinkmachine.com, item 7, check for it, we deserialize our drink. And then at the end, we can call enjoy dinner and drink. So there's some C#. Now I want to ask you all a question, which is, which UML sequence diagram does this implement? Does this implement the synchronous one or the asynchronous one? You can come off mute and speak, or however you want. Which one is this?
Synchronous.
William says synchronous. Anybody else want to vote?
The synchronous.
Okay, 2 votes for synchronous.
Synchronous.
No.
I
Yeah,
feel like I'm
same.
in the wrong now.
Yeah, so the synchronists have it, and they are right. They are right, because this call to await order dinner, it basically, it kind of blocks. I want to use that word carefully, but the point is that the second call to get your drink doesn't begin until you're done awaiting the first call. So the effect of this implementation is actually this. and not this. So that was kind of my wait what moment. When I realized that these were not overlapped, I kind of just was like, holy moly, what is the point? Why are we even doing this? Why don't I just call order dinner and order drink? Why does it all have to be async? What is it doing? So that's kind of and maybe you've had the same question. Maybe you've been like, I don't quite get why I have to do it this way. So, right, here's just that illustration that dinner, kind of the code pauses here, and then it moves on to the next line. So the rest of the talk is kind of unpacking this, like what is really happening. It turns out that async programming does do something really important, right? We can't stop doing Async-Await, but it may be a little different than what you think. And so that's where we're going to go from here, is kind of explaining it. But before we do, I did want you all to like get a look at the katsu that I got. I got the chicken pork combo. It was pretty amazing. And this is like normal Japanese person food. I know Japan has all kinds of incredible cuisine, sushi and izakaya, and it's all amazing, but a basic katsu with a curry is pretty core Japanese food. If you get a chance to go, I recommend it. And now that you're all really hungry, I'm going to keep talking about C#. So, okay, so what does Async-Await actually do? And the answer is, it's really all about the thread pool. So to explain this, let's begin with a little thread pool that has exactly 3 threads. Now, I know when you start a .NET application, you get thousands. It's just, it would take me too long to draw all the boxes. So we have a thread pool with exactly 3 threads. And now, let's say you have some kind of server, some process that is receiving requests. And every time your application gets a request, it fires up a request handler. So you're using the task-based programming model. This is a task. And when your task starts running, a task gets assigned a thread pool thread. So your first instance has got T1 assigned to it, and your code is running on T1. Now, let's imagine that your code has a couple of steps that are just like really fast in memory, but then we get to step 3, which is kind of slow, which is going to wait on something else. And so this request is kind of hung here for just a little bit. Meanwhile, we have a couple more requests that come in. Request 2 gets T2, and request 3 gets T3. And so now you've got 3 request handlers going, 3 tasks running, and your thread pool has been exhausted. So what happens when a 4th request comes in? The reality is, in this situation, you will get thread starvation, and request 4 can't be serviced. It just has to sit there and wait till one of these threads becomes available. So thread contention and thread starvation, where your different request handlers are fighting for a limited resource, that is the problem that Async-Await solves. That's what it actually solves. So how does it solve it? So let's go back to the original scenario where our first request came in. We'll just go back in time. So what an await statement in your code does is it creates this cool thing called a continuation. And a continuation is kind of like a bookmark. And the way it works is this. You get to step 3, and rather than just executing it, you await it. You call it asynchronously. And so what happens is the framework kind of says, okay, that task is kind of needs to wait a little bit on something to finish. So we're going to let its thread return to the thread pool. We're not going to sit on that thread while we're waiting. And we're going to set a bookmark there, a continuation, so that when the result of that await comes back, we know where to restart, where to continue. And we'll rehydrate that one and give it a new thread. So there's kind of a magic signal that tells the framework that, okay, you're ready to go. You can rehydrate that one, but we'll get there. For now, what you need to understand is that the await lets your thread go back to the thread pool. So now next, if in the next step, we got those 3 requests, they all began running, they're all awaiting at step 3. We have 3 lovely threads in our thread pool, so that when my slides are out of order, why did that happen? Okay, so that when the 4th request comes in, there's no problem. It can be given a thread pool thread. So thread starvation or thread contention is solved. So that's what Async-Await does. That's its purpose. To just kind of complete the story about the continuation, let's now say that await on step 3 completed. You got the HTTP result back or whatever it is you were waiting for. You got the magic signal that, okay, it's done. So what happens then is the continuation is cleared, the request is kind of rehydrated, and it's assigned another thread pool thread, and then it can continue and finish out its work. One thing that I did intentionally here is you'll notice that request 1 began its life being serviced by thread 1. After the await, it continued on thread 3. That's really important. There is no affinity between a task and a thread pool thread. A task is always running on a thread pool thread, but you can't say which one, and it may switch in the middle if you have awaits. So that's why techniques that you may have bumped into, like thread static, are a complete disaster here, because you can't count on thread affinity in your tasks. You just are given the thread you're given. And if you trace this out, you can watch this happen. It's actually absolutely shuffling the threads about and allocating them through some algorithm that, I don't know. So that is what it does. So in summary, Async-Await doesn't allow the code inside your function to do multiple things at once. That's what I thought it did, but that's not really its purpose. Rather, it frees up thread pool threads so your application overall can do multiple things at once. Now, if your application is a little console app that's just, crunching some numbers and it doesn't have thousands of requests, you might think, oh, that's totally irrelevant. That doesn't help me. And that might be true. I have a feeling that where this came from, I have no evidence to back this up, but my hunch is this came as a requirement from the ASP.NET team. Because if you build an ASP.NET web service that's not async and you scale it up, that's a situation where you quickly do overwhelm the thread pool. So this is a real world bottleneck. And my hypothesis is that team said, hey, framework team, we need some way to cope with this. And they invented Async-Await. And now it's used lots of other places, but this is what it's really for, is thread pool load balancing in a high throughput, many request application. So maybe that's a surprise. Maybe you knew that all along. For the rest of the talk, what I'd like to do is kind of unpack the implications of that. There's a lot of follow-on thoughts, but right before I get into that, are there any comments, questions, things you want to make sure I address as we go forward?
None in the chat so far.
So far, so good? Okay.
Doing great.
Right on. I'll just keep motoring then. So here's the implications and analysis. Now, at the beginning, I kind of said what I want is something that overlaps my async calls. And you absolutely can do this. It's not that C# has no way to do it. So here's a little code which gives you the overlapped or parallel async implementation of get dinner in Kyoto. So what we do is we call order dinner, but we capture the task that it returns. And we call order drink, and we capture the task that it returns. And then we call await task dot when all. and we pass in the array of tasks that we're awaiting. So now both order food and get drink will kind of go in parallel, and you only enjoy your dinner when they've both completed. So that's how you get the best of all worlds, right? Where you're not sitting on thread pool threads, and you're optimizing your code's ability to make multiple parallel requests out into things that are awaitable. So that's a little code snippet that may be helpful. The next kind of implication is what I call, I'm using turtles all the way down for this. So that's a little catchphrase that refers to the problem of infinite regress. So here's an experience that maybe you've had. Let's say you've got this lovely program. Main calls function 1 calls function 2 calls function 3, and everything is perfectly happy. Then one day you realize that function 3 really needs to do an HTTP GET. It needs to do something async. So you now change this. So this is now static async task function 3, and it does its stuff. But this creates a problem because now function 2 can't compile because it's not async. So what do? Well, you fix function 2 to make it async. Well, that causes a problem for function 1. And it basically ripples all the way through your entire application, all the way back kind of to the root, to the entry point. So it's almost like as soon as you add one async thing anywhere, all of a sudden your entire program has to be declared as async. I don't know if anyone has experienced this. So this can be kind of frustrating and difficult, especially in a large legacy code base where you're like, I really don't want to declare everything async. So what do? How do you handle this? So the reality to be aware of is there is always a synchronous, asynchronous boundary. Your Windows program is fundamentally synchronous in terms of its relationship to the operating system, right? The Windows OS or the Docker container running on Linux OS or whatever it is, it doesn't understand what a C# task is. So when it calls main, that is going to be static void main. It's not going to be async. Now I'll come to how there is a way to do that. But basically, until pretty recently, you were stuck with static void main in this kind of app. So what you do is you call your first asynchronous function, function 1, .getAwaiter, .getResult. And now you're calling an async function from a synchronous call context. There are some other syntaxes that are out there in terms of creating the task and then awaiting it. There are a few other ways to do it, but my understanding is that this is the safest way to do that. So that's how you negotiate the synchronous asynchronous boundary. And the key here is you can do that wherever you need to. This is a little like exception handling. You probably want to look at your overall architecture and make decisions about where exactly you are going to do that. But you do get to choose if you want to. So that's how you do it. Now, the other thing you can do in the latest, I think this is since, I can't remember if it's C# 9 or 10, they actually support async main methods in a traditional app. And of course, if it's an ASP.NET application, you can declare all of your controllers, all your web service controllers as an ASP web service, I should say, not .NET. That shows how old I am. You can declare all of your web service controller methods as async. So in that case, the synchronous asynchronous boundary is handled for you before your code starts running. And here it's also handled for you. And what's happening is the .NET, when you compile it, the IL that's emitted, it could probably contain something like this, like the invisible main. This is the actual entry point that the operating system calls, and it does getAwaiter.getResult, calling your sort of fake async task right here. Again, there's always a transition. You should know when it's happening automatically, and if you want to take control of it, you can. So that's how you handle turtles all the way down, the async infinite regress. So the next thing I want to get into is the question of what actually makes something awaitable. Can you await just anything? Is there a point to awaiting just anything? So to answer this, we have to go back to our computer science class and refresh our memories on the difference between CPU-bound work and IO-bound work. So CPU-bound work are tasks that are limited by the CPU's processing speed. Basically, your performance will improve with faster cores, more cores, and optimized algorithms. The characteristics of this kind of work is high CPU utilization, often involves computations like math, machine learning, sorting. You tend to see long CPU bursts with minimal IO. And the way you optimize these is with multi-threading or algorithmic efficiency. So I've written some of this code. I worked on a biotech app where we had several things that needed this. We were doing some nonlinear regression, and it involved, and we also were doing some flow cytometric compensation, which is giant matrix multiplies. And another one that was pretty taxing actually was calculating medians on very, very large data sets because you have to sort them. So all of those tasks, which are all very mathy, were CPU bound, and we handled them by using multi-threading. And at the time, we actually were doing threads, but then we ported it to tasks to let the task system load balance. But basically, if that was running on a 4-core machine, you were only doing 4 at a time, and the cores were pegged while it was doing that. So that's CPU-bound work. IO-bound work, in contrast, are tasks or work that's constrained by input-output operations, such as disk reads, and for us, almost most commonly, network requests, or database queries, which are just a flavor of network request for most of us. So the characteristic here is low CPU utilization, frequent short CPU bursts interrupted by long IO waits, like get async, and now we're just waiting. And performance improves with faster storage, faster network bandwidth. But sometimes you can't improve performance because the bottleneck is on the other side in the thing you're calling. So basically, your optimization here is to use asynchronous IO, which is what we're talking about. So Async-Await is all about the IO-bound stuff, not about the CPU-bound stuff. We're talking about awaiting IO requests. And if you look through all the different .NET core namespaces and the NuGet packages, and you look for methods which are marked, usually named async, and marked as async task. In other words, they're awaitable. If you look at them, they all are things like system.net.http, get async, patch async, post async, put async, delete async, or SQL data client, open connection async, execute reader async, execute scalar async, Azure messaging service bus, send message async, send messages async, schedule message async, cancel scheduled message async, receive message async. So almost all of these are actually TCP, usually network stuff. Now, there is some named pipes if you happen to want to do that, if you've got some old WCF code. There's, of course, your traditional disk I/O, but they are all I/O. So what's going on here? What is happening? So you remember I said when the continuation gets set, that the framework starts listening for kind of a magic signal that it's okay to rehydrate the request, give it a new thread, and move on to step 4. Well, what is that magic signal? So the magic signal on Windows is actually an operating system level function called IO completion port, IOCP. What that means is that in Windows, if I'm going to do a a TCP get, right? Or a disk read or something that's IO related, I can call it using IOCP, which means the operating system says, okay, I got that request. You can have your thread back. And here's a port you can listen on, and I'll let you know when your request is done. That's the magic. And it's happening at a very low operating system level. Okay. You can actually decompile this. You can, I mean, well, it's a lot of, pinvoke, import Windows functions kind of stuff. But you can imagine, if you've ever done that, you can imagine what this looks like. But this is the low-level interrupt between .NET and Windows. So basically, IOCP allows the caller to initiate an IO operation, subscribe to a special port that will signal them when the operation completes. That is the magic secret sauce that makes something truly awaitable. All right, so one last thing, which is, what about CPU-bound work? And in my experience, I've given this talk now probably a half dozen times, and sometimes this can be a little sand trap, because when people think about parallel programming, this is where your mind goes. You're like, oh, multi-threading, and that's all about CPU-bound work. And it's really a different animal. But as I think we know, you can use tasks to run these. You're just not really going to await the individual steps. So here's an illustration of using tasks to parallelize a bunch of CPU-bound work. So I've got a little class here called job info. I've got a job ID, a decimal seed, a number of iterations, and some string, which is the data we're going to work on. So we're going to do something very mathy and painful to each one of these. And down here, I have this function, void do a job, where you pass in the job, and this is where we crunch the numbers, whatever hellacious thing we have to do. Notice that it is not async. It's just void do a job. Then in this middle, we have kind of a thing that queues up a bunch of work. So we call get work to do, and it goes out to the server, wherever, and it says, oh, I've got these 200,000 jobs to run, or these 3 jobs to run. It basically builds you a list of job info based on whatever. So here is our cool dispatcher, okay? We say list of tasks is new. We're just initializing a task list. And then we say for each job info in get work to do, could be 1, could be 100,000, create and run a task by calling task.run, passing in the do a job delegate, or the, basically the arrow function here. It's a little lambda. And then add that now running task to the list. And then at the end, you can say await task.whenAll. So if there were 10 of these, they would all get added to the task list, and they would all start running, or they would all get sent to the TPM, right, to the task programming model. And then when they're all done, your code can keep going. So here's the key. The magic here is task.run. That's how you execute CPU-bound work, non-IO, non-async awaitable work in the context of a task. And what's lovely about this, let's say this is running on my laptop, which has 4 cores, and I gave it 20 jobs to do. If you trace the thread pool, you'll see it doesn't start all 20. It'll start maybe 6 of them. And it'll service those 6. And as they start completing, it'll then start feeding it new ones. So the framework in this case is really good at load balancing for you, at dispensing the work when the hardware can handle it. And I suppose if this was running, up in an Azure function where you have access to a lot of hardware, it would do the same thing. It would like optimize to whatever that whatever kind of your CPU plan with Azure was. It would figure out how many cores it could access, and it would load balance. So that is a beautiful thing. You should use tasks to run your CPU-bound work. You're just not going to await them individually. You can await the whole thing, and that frees up one thread pool thread. but the threads that are crunching these, you're using them. They are active. Now there's a really beautiful way to do this using the often overlooked C# parallel for statement. So here's the same code implemented with parallel for. We've got our job info. We have our thing that builds the list. We have our traditional do a job method. And then here we can say list of job info, jobs equals get work to do. And then parallel dot for each, jobs, job, arrow function, do a job. There's your lambda. So this actually does the exact same thing as this, because what parallel for each does is it takes all of your job, all of your things that you're going to run, packages them each in a task, executes them all, and awaits the result. It's amazing. So you get that whole thing with a single line of code. All right, so to kind of wrap up and summarize here, we're getting towards the end. Async-Await doesn't do what I thought it did. Are you surprised too? Maybe. It uses IOCP and continuations to free up thread pool threads when doing lots of IO bound work. This allows a high performance app to service many clients in parallel. You can run tasks in parallel using task.waitAll. That's easy. There is always a sync-async boundary, even if it's invisible. And if you need, CPU-bound work can be parallelized with or without the await. You just need to know it's doing a little different thing. So there you go. There's wait what, Async-Await. And that's the end of my slides. I can stop the slideshow. We can stop sharing. I'll bring it back up if we need to look at some of the code there, but let's just open it up for questions and conversation. Thank you, Elsa.
Oh, thanks, Matt. Hey, does anyone have any questions that they want on the recording? Because we have the recorded part of the Q&A, and then we stop the recording, and then we give away prizes or prize, and then we continue doing Q&A. Does anyone have any Q&A that they'd like to do for the recording?
I'll ask one just for the greater good. That task when all, Matthew?
Yeah.
When you have a number of different tasks in there, and some of them may have failed or thrown an exception, what's the process for that? Because I'll be truthful, I don't use when all very much.
That's a brilliant question. That is spot on. So one of the and I'll try to give you a thorough answer here. So let's just take a step back and imagine you were doing traditional threading. You created a thread, you handed it a thread proc, and you kicked it off. What happens? Does anyone know what happens if that thread, that worker thread, throws an unhandled exception? If you don't have a try catch and it throws. Anybody know? It kills your app. Your app crashes. It just dies. So when you're doing traditional threading, it is up to you to, in your thread proc, try catch, get the exception, and somehow communicate it back up to the caller, right? Through thread safe data transfer of some kind, however you're doing that. So tasks do a lot of magic for you. This is another benefit of tasks. If your main code creates a task and starts it running, and the task procedure, like the main task function, throws an unhandled exception, first, your app does not crash. That's a benefit. Second, the framework, I keep calling it the framework. It's like the runtime, the magic of C#. It actually marshals that inner exception. It marshals it back up to the calling thread or the calling task for you. It's amazing, right? Now, if there is a single one, you literally just can try catch and you will get the exception. It just works. It just works magically, just like you called a function and did try catch and got the exception. It kind of reconstitutes the call stack, even though that's completely virtual, right? It's totally like a construct. And there can be certain situations where it can be a little hard to like debug and figure out exactly what happened, but it does a good job. Okay, so what happens if there are multiples inside there, right? You've run 10 of them, 7 succeeded and 3 of them threw. What's going to happen? So you get a special exception type in your caller. If you do try catch, the exception type is going to be, I think, a composite. I don't remember the exact name. It basically means a lot, more than one thing failed. A composite exception.
Aggregate exception.
And I think it's an aggregate exception, right? And inside that aggregate exception, you will have a list of the exceptions. So you can then go iterate through them and be like, okay, I kicked off 10, these 3 failed. But the beautiful thing is, if you put the data you want to communicate back in the exception, it'll just get marshaled across that boundary for you. You don't have to do any extra work. I mean, you have to know to look for it, unpack it, and do something coherent with it. But getting the data back from those failed threads to the controller thread or task is handled for you. It's very awesome the way it works. Great question. Love that.
Boy, it's hard to follow that up. Does anyone have any other questions?
I'm kind of curious, Matthew, great presentation. I'm wondering, do you have any tips for debugging multiple threads?
Yeah. So in the world, as way back at the beginning of the talk, I was like, hey, there's these different paradigms for parallelizing your code, right? Multi-threading, concurrent programming, task programming, asynchronous programming. If this is something that you are interested in, I'm going to do a little self-promotion here. I have I think it's 12 or 13 YouTube video series called Threads. And it really goes through, it's not comprehensive, okay? But it will take you through how to make a dedicated thread, how to use the old task runner class that's part of Windows component model, different things, how to safely interrupt a thread, basically how to implement cooperative cancellation. And one of the topics is how to manage exceptions and data transfer in these different contexts. So maybe go take a look and you'll get some thoughts. Really, the problems are all the same. Like, okay, something bad happened in my worker thing, whether it's whatever it is, that needs to safely communicate that to the caller. How do I do it? And the way you do it is a little different depending on what kind of worker thing you've spawned. And then once you know that you have choices, you get to make a decision. And I would say most of the time tasks are your friend and it's a very low risk, like that's option A. But there are still real world scenarios where I would opt for explicitly created dedicated worker threads, particularly in very long-lived processes where you want thread affinity and you want to control the life cycle. So, you have questions there, but that's a great question. And go watch some of those videos. And then if you're like, could you explain more or do a follow-up? That's how I get new ideas for content and stuff. So I would love to hear from you.
Thank you. I'll definitely check out the channel.
All right.
Cool. Other questions?
Right on. Thank you all so much. I really enjoyed it. And again, be in touch and good luck on your journeys as C# programmers, as artisans.
All right, and if you are watching this on YouTube after the fact, know that the link to Matthew's courses are down below. So stopping the recording now.